Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. Before starting my presentation, I would like to introduce myself. My name is Bukaud Ablali. I am a doctor from the University of Medaya. The title of my presentation is UV spectroscopy and computational study of structural, electronic, and optical properties of benzoic acid. The outline of my presentation are divided into 4 parts. First, I will start by a brief introduction in order to define the objective of my study. Then, I will present to you some important notion of molecular spectroscopy, especially infrared and UV visible spectroscopy. In part 3, I will present to you the application of DFT calculation on benzoic acid. Here, I concentrate on the structural properties, vibrational properties, electronic properties, and optical properties of benzoic acid. And finally, I will give you our important conclusions. Benzoic acid is an important compound. It occurs naturally in different foods such as fruits, vegetables, species, and nuts. In the food industry sector, it is widely used as preservative in acid foods. In this study, the structural, electronic, optical, and spectroscopic properties of benzoic acid have been investigated using density functional theory DFT performed in the solid state. Our calculation has also compared with the experimental one obtained by using infrared and UV visible spectroscopy. The structural properties is also compared with previously published data about the crystal structure of benzoic acid. Let's start by molecular spectroscopy. It is well known that spectroscopy is defined as the area of science which is based on the interaction of electromagnetic radiations with molecules. Here we can see the electromagnetic spectrum. The spectrum is divided into several parts. In each wavelength region, we can define a technique. For example, for the X-ray region, we can define the diffraction technique. For the UV visible region, we can define the electronic spectroscopy, which is the UV visible spectroscopy. In the infrared region, we can define the vibrational spectroscopy. For this region here, in the microwave region, we can talk about rotational spectroscopy. For the radio TV region, we can speak about the RMN spectroscopy, resonance magnetic nuclear spectroscopy. The question now, what do we see before the interaction? Here we can see the interaction of this molecule with the electromagnetic radiation. The response of the molecule is generally traduced by a curve called the spectrum. The spectrum is represented here. Our main objective is to obtain the significance of each bond appeared on the spectrum. Let's start by IR measurement. We have used the Cabier disk technique. Here we can see the infrared spectrometer used in our measurement. The Cabier disk is placed here in the direction of IR beam. Before the measurement, the IR spectrum is presented here. For the UV spectroscopy, we have used this spectrophotometer. This figure represents the UV spectrum of benzoic acid, the spectrum shows two fundamental bonds at 238 and 272 nanometers. Before interpreting the experimental data, I would like to show you some slides about the fundamental of density functional theory. This theory is based on the resolution of the Schrödinger equation Hpsi is equal to Epsi. Here we can see the Hamiltonian, which is the addition of several terms, the kinetic energy T, and the kinetic energy for nuclei, and the Coulomb interaction nuclei electrons, and the Coulomb interaction electrons, and the Coulomb repulsive interaction nuclei. The resolution of Schrödinger equation is not possible, and we need to make some approximation, like the Born-Oppenheimer approximation. The key idea of density functional theory is the electron density is a positive function of only three spaces variables. If we know the density, we know the Hamiltonian, and if we know the Hamiltonian, we can solve the monobody Schrödinger equation and know everything about the system, all properties. In our calculation, we have used the GGA approximation. This approximation is used to obtain the exchange correlation potential. Let's start by the structural properties. We can see here the unit cell optimized by DFT calculations. All the calculated parameters are represented here. These parameters are in very good agreement with the experimental one obtained by using X-ray diffraction technique. The structure is used to calculate the other properties like the electronic and optical properties. In order to explain the experimental infrared spectrum represented here, we have calculated the frequency by using DFT calculations. This region is generally assigned to stretching vibrations. We can see here the CH stretching vibration at 3129. Here we can see the OH stretching vibration at about this region, and here for this bond we can see this vibration. This vibration is generally assigned to CO vibration. The electronic properties are obtained experimentally from the UV visible spectrum. The gap energy is calculated to be 5.01 electron volt. Here we can see the bond structure of the benzoic acid. The gap energy calculated by DFT is obtained to be 3.6 electron volt. This underestimated is explained by the approximation of DFT. For the optical properties, we have calculated the refractivity and the absorption for the 100 polarization direction. For the refractivity, we can see here a strong bond at 6 electron volt. For the absorption, at approximately same bond position, we can observe strong bond too. The refractive index and dielectric function have been also calculated for the same direction. The red curve represents the N and the blue curve represents the K. Here The red curve represents the imaginary parts of dielectric function, and the blue curve represents the real part of dielectric function. In the same polarization direction, the conductivity is also calculated. Here we can see the real and imaginary part of the conductivity. The real part is represented by the blue curve, and the imaginary part of the conductivity is represented by the red curve. Conclusion. In this study, density functional theory calculation performed in the solid phase have been employed in order to study some structural, spectroscopic, and optical properties of benzoic acid. The optimized unit cell is obtained to be in very good agreement with the corresponding one obtained experimentally. The gap energy is obtained both theoretically employing DFT and experimentally by using UV spectroscopy. The experimental infrared spectrum has been recorded and interpreted basing on DFT calculation. Some optical properties like the refractivity, absorption, refractive index, dielectric function, and conductivity have been also calculated. Thank you for your attention.